This is the Further Maths Support Programme Wales Year 11 to Year 12 Bridging course on integral calculus, also known as integration, and it follows on from the first session of differential calculus, which was posted at the start of June. I'm going to split the session into 3 parts. First, I'm going to show you the technique of integrating certain types of expressions which you will need to do in year 12. Then we're going to use this technique to work out the equation of a curve if we're given the gradient of the curve at a particular point and what the coordinates are of the point where we know the gradient. And in the third part, we're actually going to use integration to work out the exact area under any graph, which is one of the main reasons why we do integration. Again, just like differential calculus, it's an extremely important area of mathematics, and you will, any STEM subject you may do in university, you'll be seeing this extensively. In A level, again, it's something that you will look at for a considerable length of time, especially in year 13 as well. And if you do study further mathematics, again, there'll be a lot of integration that you will cover, as it is used a lot in, for example, mechanics as well. So it's a very important topic. Okay, so before I go straight into part 1, I'll just give you a quick overview of what integration is about. So what you know from your GCSEs is the following. So if I was going to ask you to work out the area under the graph, in this case it's y equals 18 plus 3x minus x squared, and I want you to work out the area between the x values 0 and 6, what you learnt in your GCSE course was to split the graph into strips and make them into essentially trapeziums, and at the end here you can see it's a triangle, but it's using the trapezium rule. So this method you are in theory aware of. So we split it into trapeziums, and then knowing the area of a trapezium, which is a formula that you do know and actually given in the exam booklet, you work out all the areas, and then unsurprisingly you add them up, and in this case we get an estimate of the area of 89 in units, because we haven't actually specified what the measurements are. So it's got an area of 89 units, but as you can see in this graph as well, it is an approximation, it's an actual underestimate, isn't it? Because if you look at, for example, strip B, you can clearly see that what we have is a rectangle there and the curve actually goes over it. So the area that we've got is definitely less than what the actual area would be of this graph between 0 and 6. Now some of you may be aware of the formula as well, so I've just added that for completeness. Again, if you put these values in of the y coordinates, you will and should get the same value, which is 89 units. But as I said already, this is an estimate. It isn't the actual area of the graph between these two ranges. So what is the actual area under the graph between x equals 0 to 6? Well, what we do is we use the technique of integration. So this is how I write it. So if I'm going to integrate the expression 18 plus 3x minus x squared between 0 and 6 with respect to x, the mathematics behind it is what we're going to learn in the next part of the course. We get an answer which in fact is 90. And by integrating the expression, this actually gives us the correct answer. So you can see now that the actual area is slightly more than what we estimated before using the trapezium rule. Only by 1, but that is an estimate, and this is the actual specific area of the graph. So this is what we're going to learn. This is the technique of integration. So in the first part, I'm going to show you how to integrate an expression. And I'll explain to you shortly what indefinite integration means. Okay, the first thing I want you to make sense of immediately is that integration is the inverse of differentiation. So what we know of differentiation from the last recording is that if I ask you to differentiate x to the power of n, where n is any number, what we did was you multiply by the power, then you take 1 away from the power, which leaves you with the differentiated expression of n times x to the power of n minus 1, where n is any number. So this is what we learnt in the first session on differentiation. So therefore, if I've just told you that integration is the inverse of this, if I ask you to integrate x to the n, well, the first thing I do therefore is add 1 to the power, and then I divide by the new power. And my result, therefore, is x to the power of n plus 1 divided by n plus 1. Again, n being any number. So how do I write this mathematically? Well, this is what we do. So there is the integral sign. It's like a big S shape. And it is to do with summing, because integration is essentially to do with adding those strips we saw a few slides before with the trapezium rule. Now, as in with differentiation, you needed to know why it works. If you can recall differentiating from first principles, you do not need to know that for integration. But again, it's very similar. It's to do with having these strips under a graph and making the widths of the strips smaller and smaller to a limit where the strips are actually of 0 width. And once that happens, your adding becomes integrating. So that's the process. But like I said, you do not need to know this for this course. But there is the integral sign. So how do we say this? Because there is a way of saying this, because you've got a dx there. Now, obviously from our algebra knowledge, things next to each other, we mean multiplying. This doesn't actually mean it in this case. What this is saying is I'm integrating x to the power of n with respect to x. So x is my variable, there's the unknown, and I'm integrating the expression with respect to that letter, so with respect to x. And there it is. So there is my x to the n plus 1, all divided by n plus 1. And then we also add this extra letter plus c. Now, it's a capital C we generally use. It doesn't have to be C. But the reason it is C is just for no surprise other than it's called the constant of integration. And this must be included. It's very important that you add this to any expression when you integrate, and doesn't have the limits. You'll see in due course the numbers at the top and the bottom of the S sign. This is what makes it indefinite. All you're doing is integrating an expression and you add the C at the end, and that is the final answer. And it's very important you add that. If I'm talking just exams, if you don't include that extra letter, that plus C, you do lose a mark in your exam. So it is important, and there is a mathematical reason for it, as you will see in the next part of this video. Now, I did say n can be any number, but there is one number that doesn't work for this, and that's if n is minus 1. Now, I want you to just have a quick think why it can't be n minus 1. And if you don't want to know the answer immediately, if you want to just quickly stop the recording and just have a quick think before I tell you why. So if you want to stop the recording now. Okay, the reason is because if n is minus 1, we get 0 as the denominator, and we know that it is not possible to divide by 0. Okay, I'm going to show you some examples on how to integrate certain expressions. So here's the first one. So I'm going to integrate 3x squared with respect to x. And remember the technique, it was you add 1 to the power and then you divide by the new power. So there it is, there's the answer. So I add 1 to the power, so 2 add 1 is 3, so you've got x cubed, and then you divide by that 3. Now, because it's 3x squared is the expression, if I divide by 3, you can see that the 3's cancel. Yeah, 3 over 3 is 1, so you're left with x cubed. And don't forget the constant of integration plus c. There's the first one. Integrate x to the power of 6 with respect to x. Add 1 to the power, divide by the new power. So we've got x to the 7 divided by 7. Add c. Now I just have a number, 7 here. Could be 1, it could be any number again. Now if I integrate a number, a constant, essentially we just have to add the x to it. And then the plus c. So any number just becomes the number times x. And if you think about that carefully, why does that follow what I've just done in the first two examples? Well, 7 is the same as 7 times 1. And we know that 1 is the same as x to the power of 0. So basically by integrating 7, I'm actually integrating 7x to the power of 0. And now I can just follow the method for the others. So 0 add 1 is obviously 1. So you've got 7x to the 1, and then if you divide by 1, you've just got the expression as it is. So that's why it works. So number integrates to number times x. Any expression with multiple terms, you just treat each term separately. So 3x to the 4 plus 5x minus 2 becomes this. So add 1 to the power. So 3 is not obviously a multiple of 5. So you've got 3/5 x to the 5. Same with the 5x. That becomes 5x squared over 2. And then the minus 2 becomes minus 2x. Add c. Right. Here I've got 1 over x squared. So what we've always got to do is write each term, in this case a single term, into a power. So we know that 1 over x squared is the same as writing x to the minus 2. They mean the same thing. So now that I've got it as a power, I just follow exactly the same process. Be careful here. Minus 2 add 1 is minus 1. I do see this quite often, just careless mistakes where you go minus 2 add 1 is and minus 3. Just because you see it in a different way, it is an error that I occasionally see. So just be careful there. And then dividing by minus 1 is the same as timesing by minus 1. So there are the different ways. So you've got minus x to the minus 1 plus c. Or if I write it not with a negative power, it would be plus c. Right, so there's that one. Now I've got the root of x. Again, I've got to change it to a power. So we know that the square root is the same as to the power of a half. And then exactly the same method is used. So a half add 1 is 3 over 2. So then I've got to divide by 3 over 2. Now, dividing by a fraction is the same as multiplying by its reciprocal. So the reciprocal of 3 over 2 is 2 over 3. So you can now see that this becomes 2 over 3 times x to the 3 halves plus c, and then to write it in a shorter, neater mathematical way, that's the same as 2x to the 3 halves over 3 plus c. And if you want to write it as powers and roots, well, the 2 is the square root, so you've got the square root of x, and the numerator of the power, the 3, means it's cubed. So you've got 2 times the root of x cubed over 3 plus c. So these all just mean the same thing, and I'm just writing it for you in different ways. Right, so now there's showing this one as a combination. So I've got 5 times the cube root of x. So that as a power is 5 times x to the power of a third. Again, a third add 1 is 4/3. Note how I'm not using mixed numbers here. I'm leaving it as an improper fraction because that means I can easily interpret what I have to do with the x. In this case, to the power of 4/3 means cube rooting the x and then raising it to the power of 4. So there we are. So you've got 5x to the 4/3 divided by 4/3, which means I'm multiplying by 3/4, the reciprocal of 4/3. And then I can then tidy that up. 3 times 5 is 15 times x to the 4/3 over 4. And again, another way of interpreting this is 4/3 is the cube root of x to the power of 4. Okay, so here is an exercise for you to try. I've got 8 there. So please have a go and stop the recording, and then I will show you the answers. So stop the recording now, please. And here are the answers. Right, we are now going to use integration to work out the equation of a curve, knowing a point on the curve and its coordinate, and the gradient at that point. So, we are given the gradient dy by dx equals 5 minus 2x at any point on the curve. That's the gradient. So wherever we are on the curve, if I know the x coordinate, I can work out what the gradient is at that particular point. So there's the gradient, and we've also been told that there is a point on the curve with coordinates 1, 7. So there's the setup. So we need to work out what that black curve is. What is the equation of the curve? So because we know that integration is the inverse of differentiation, if I integrate the gradient, if I integrate dy by dx equals 5 minus 2x, what we actually are given is the y, because integration is the inverse of differentiation. So this gives us an expression for the curve. So y is equal to the integral of 5 minus 2x with respect to x, and then following the technique we've just learnt, we work out that the gradient of the curve, the actual equation of the curve is y equals 5x minus x squared plus c. So remember, we have got, this is indefinite integration, so we have to add the c to the end. And now you can, this following part, you will understand why we have the add c. Because at the moment, we don't know where this c could be any number. We've got the expression 5x minus x squared, but we don't actually know where it is, because the curve could be anywhere on this xy axis, on this xy coordinate grid. So now, using the fact that we know a particular point on this curve, which is 1, 7, I substitute that into the equation y equals 5x minus x squared plus c, where we know that y is 7 and x is 1, and that now, by rearranging, gives us what our c is. So this c has now been worked out, and we have the constant of integration as a particular value. So by doing that, we now know exactly what the equation of the curve is. It's y equals 5x minus x squared plus 3. And if you remember your differentiation, if I quickly differentiated that expression, you do get 5 minus 2x. And 1, 7 does work in that expression, so the point is on there. So here is an example of using integration. Okay, I've got two examples for you to try. So here's question 1. So please read it carefully and I will stop the recording and then you can have a go and the answers will come shortly. So stop the recording now, please. Here's a solution and answer. Here's question 2. Please stop the video before I show you the answer now. Part 3, the last session, I'm now going to show you how to find the exact area under a graph, which is definite integration. And I briefly mentioned it at the start of this video. So in this session, again, we're only going to focus on expressions with x to the power of n in them. Okay, so here is an example of a curve. This isn't the actual curve y equals x to the n, but I'm just showing you here is a curve, some combination of x to the n. Really, I should be writing here y equals f of x, but there it is, x to the n, and I want to work out what the area is between a and b. So if I go along the x-axis and I work out the area from a to x equals b, what will that be? So we now know, I quickly briefly touched on this at the start of the video. What I've got to do is I've got to integrate, and the way you set this out now is if you look at the left hand side, so it's the integral of x to the n with respect to x between the values of a and b. So the bottom number is where you start, to where you're going to is at the top of the integral sign, there's the b. Now the actual integration part is exactly the same, so integrate the expression as we've learnt, but the difference is now is first you can see there is no constant of integration there, there's no plus c. They do actually cancel out. You could write them there, but because there's a subtraction involved, they do cancel out, which is why we don't actually have it there. So there's no plus c. This is what makes it definite. The plus c made it indefinite because we weren't sure what the c was unless we knew some extra information about it. So no c. So there it is. There's the x to the n plus 1 over n plus 1. And then what you do is you substitute in the top number, in this case our b, into the expression and take it away from the substitution of a into the expression. So there's the general case of what we do. And then obviously I'm going to show you a particular example of how it works in detail in the next slide. Okay, so here is an example from a past additional maths paper. So we've got the graph of y equals 4x minus x squared, and it cuts the x-axis at the origin, 0, 0, and 4, 0. And we've got to find the area of the shaded region. So we know the x-coordinates are 0 and 4. So the area, the actual area of the shaded region is the integral of 4x minus x squared with respect to x between 0 and 4. So you can see there are the coordinates, x coordinates in the integral sign. So now following what I've just said, so we integrate the expression, so 4x becomes 2x squared minus, so x squared becomes x cubed over 3. And then what I've got to do is I've got to pass the 4 in to that expression and then take away the 0 passed in to the same expression. So there it is, that's the number part here. So we've got the 4 going in there, so we've got 2 lots of 4 squared minus 4 cubed over 3. We work that out on a calculator or in your head obviously, and then now I've got to substitute 0 in the bottom number, which is the x equals 0 coordinate, into the expression, and then we get a final. Now obviously sometimes it's quite easy because all the terms in that second square bracket a naught, aren't they? Anything times by naught is naught. So the first one is you basically don't even have to work out because it's just nothing. But there it is, and what we get is an answer of 32/3. So that is the actual area of that quadratic graph between 0 and 4. Okay, so as before, I've got 2 questions for you to try. So here's the first one. So please stop the recording if you don't want to see the answers first now. And the solution and answers are here. And here is question 2. So please stop the recording now. And here are the answers. And that's the end of this session on integration. Thank you. Diolch yn fawr.